Okay, so today we're going to be going over the cross-sectional volumes. Okay, but I want to start off by doing some setup work. Okay, so the first part of this asks you to write the formulas for the area formulas for the following shapes. So when we look at this square, the regular area equation is s squared. But for this specific shape, the area is going to be b squared. Okay, because the base of this square is b, since it's square all sides are the same, so b squared. Same thing for the semicircle. Normally it would be pi r squared over 2, or you could write it as pi over 2 times r squared. Now in this case though, for this semicircle, the area is going to be pi over 2 times b over 2 squared, because the base is the diameter, so the radius is 1/2. And when you simplify, you get pi over 8 b squared, because b over 2 squared would be b squared over 4 times pi over 2, which would be pi over 8. Okay. Now a rectangle, the normal equation is base times height. But for this specific rectangle, the height is 1/2 the base, so it's going to be base times 1/2 the base, which is 1/2 base squared. Hope you start seeing the pattern soon. Now, an isosceles right triangle with the base as a leg. So the original area equation is 1/2 base times height. But for this triangle specifically, since the leg, it's an isosceles, this leg and this leg are the same, we get 1/2 base times base, which is 1/2 base squared. Now, the same triangle now, with the base being the hypotenuse, think of it this way: if we drop an altitude here, and this is a 90-degree angle, if it's an isosceles right, it's already a 45, 45, 90. When we drop this altitude, this becomes my 90, and my other two are my 45, 45. The altitude also cuts this side in half, which means if this side's 1/2 b, then the height for this is going to be 1/2 the base as well. So using that same area equation from the last one, the area for this one is going to be 1/2 base times the height, which is 1/2 the base, which gives us 1/4 b squared for the area of this triangle. Okay? So the first thing you notice that all of my areas are now in terms of whatever the base is, instead of their individual equations. And that's going to help us when we start moving through these cross-sectional volumes. Okay? So let's look at our first problem. It says we have an area bounded by the x-axis, x equals 9, and the square root of x. The bases of cross-sections are perpendicular to the x-axis. So as soon as you hear that, you know that you're using this equation. The integral from a to b of the area in terms of x dx. Okay? Now, it's always helpful to draw kind of an idea. I've given you the 3D picture of kind of what this is going to look like. And I'm going to draw one of my squares that are going to be perpendicular to the x-axis. So you can see that here. Perpendicular to the x. And it's going to come up three-dimensionally from my function. Okay? Now, you can't really see it like this, but there are going to be a ton of these little squares here. Okay? There's going to be one there, one there. I can draw a bunch of them. Okay? And basically, it's going to create this three-dimensional volume. Now, my area equation, going back to what I have up there, the area is going to be b squared, the base squared. This, from here to here, is my base. This vertical strip should look familiar. It's what we've been doing with bounded area, which means my base is the function on top minus the function on the bottom. Okay? And this is where they link. Basically, we're taking this idea of this vertical strip that we did when we did bounded area, and we're applying it to find the length of the base for my cross-sectional volume, which really easily means that my function on top is my square root function minus the function on bottom, which is the x-axis, which is y equals 0, which means my base is basically the square root of x, which means my area is the square root of x squared. So we plug what we know in. So now that we know what the area equation is, it's going to be the integral, and this is the square root of x squared. And where does our volume start? Well, our volume starts here where the two intersect at 0 and finishes right here at 9. So from 0 to 9. And becomes real easy now because the square root of x squared is x. The antiderivative will be x squared over 2, and we evaluate it from 0 to 9, which is 81 over 2. And that's my volume. So the volume of that figure is just 81 over 2. The integration becomes very, very simple. The hardest part is the setup. Okay? And the setup comes from what we learned in our last unit on bounded area. Okay? Now, the next one, we're doing the exact same function, but now we're doing semicircles. Okay? So it's still, again, the first thing you should do as soon as you know that it's perpendicular to the x-axis, you write your equation from A to B. Since it's perpendicular to the x, it's area in terms of x dx. I'm going to draw one of my shapes just so I make sure. So it's going to be perpendicular. So here's my perpendicular to the x. And now we're going to have semicircles going like this. So this is my base, the base. So the area of a semicircle is pi over 8 b squared. And again, in this case, the base is my function on top minus my function on the bottom. So it is also, the base is the square root of x, which means my area is this pi over 8 square root of x squared. And again, we just plug in and go. So again, it's going to be from 0 to 9. The area is pi over 8 times the square root of x squared dx. Now, pi over 8 is just a constant, so we have an integration rule that says that we can just move that out, and it will multiply it at the end. So we end up with the square root of x squared from 0 to 9 dx. And we already know the answer to that. We just did that in the last problem. So basically, this is just pi over 8 times 81 over 2, which is 81 pi over 16. And that's our answer. And your code for today is UM4D question mark. UM4D question mark. So basically your takeaway here is that when we're doing these cross-sectional volumes, when you look at our area equations, and that's part of the reason we did this, basically all of my area equations are b squared, and they differ solely on some kind of constant. So when we find volumes based on those same, our volumes are going to be basically similar or even exactly the same multiplied by that same constant. Okay?